This is my presentation on Physics 2212 Lab 5, Falling Bar Magnet. This lab models Faraday's law both physically and through code by modeling a falling bar magnet through a roll of aluminum foil. The main physics principles I utilized during this lab were Faraday's law, the Biot-Savart law, and Newton's second and third law. My main results show the time it took the magnet to pass through the tube when I modeled the experiment physically was 0.952 seconds. However, the code's time prediction was 1.95 seconds, given the same parameters. Faraday's law-induced current flows counterclockwise through the roll of aluminum the magnet is dropped through. This lab asks you to take a roll of aluminum foil and in multiple trials find the amount of time it takes for a bar magnet to fall from one end of the tube to the other. To measure this, I used my cell phone in slow motion and found the amount of time it took for the bar magnet to drop. Here are some of the physical measured values I took before starting my experiment. The length of the tinfoil tube was 0.29 meters. The width of the foil was 0.005 meters. The inner radius of the foil was 0.016 meters. After 10 trials of dropping the magnet north end first and 10 trials dropping the magnet south end first, I found the averages. When I dropped the north end in, the average was 0.952 seconds. Meanwhile, when I dropped the south end first, the average was 1.002 seconds. As you can see, these values are basically the same. After taking the average of 10 trials of dropping the magnet with no aluminum tube, I found the average time to be 0.88 seconds, which you can see is much less time than it takes to fall through the aluminum tubing. In my code, I had to calculate the rate of change of the magnetic flux through each ring. I did this using an equation given from one of our lecture videos, seen on the top. For the value of mu, I used 3.45, which I calculated from our Lab 3. Y here is the current distance of the bar magnet from the ring. V is the velocity of the bar magnet. Rho is the radius of the ring. Here, the direction of d flux dt is down, because the closer the magnet gets to the ring, the greater in magnitude the flux and the field are. I then calculated current through Faraday's law. I is EMF over R. The resistivity of aluminum was given as 2.65 times 10 to the negative 8 ohms. The EMF is N times the d flux dt, which we calculated in our previous slide. Here, N is equal to 1 because we are measuring each ring separately. I then found the B field at the ring from a function I copied from a previous lab. The magnitude of the force on the ring is 2 pi r times the magnitude of current times the magnitude of the field times sine of theta. I then created code to calculate the updated position and velocity of the bar magnet. The velocity of the bar magnet can be found by adding the current velocity to the net force divided by the mass times the delta t. The position update can be calculated by the current position plus the velocity of the magnet times delta t. I will now go on to interpret my simulation. Because d flux dt is pointing down, negative d flux dt is pointing up. So by the right-hand rule, your fingers curve counterclockwise when looking from above. When the magnet is flipped upside down, as seen in my real-world experiment, there is no difference in dynamics because the times are roughly the same. The computational system calculated 1.95 seconds, given all of my same physical data. This could be made more accurate by breaking the system into smaller and smaller rings. My experiment also may have had small measurement errors due to the magnet hitting the sides of the tube and/or recording errors. The velocity versus time plot, shown here on the left, was mostly a constant value, which shows the net force is equal to 0. If the resistivity of the conductor was decreased, the magnet would fall much slower. With decreased resistance, the current would increase, and therefore the force would increase, due to the equation F equals ILV. If holes were cut into the tube, there would be a smaller number of rings in the final sum, which would make the total ring current weaker. In conclusion, Faraday's law induces a current that creates an opposing magnetic field to the one produced by the bar magnet. The time it took for the magnet to fall through in the aluminum tube in real life was slightly faster than what was modeled on the computer, due to slight errors in the physical lab. The magnet falls slower inside the tube versus outside of the tube because the tube has an induced magnetic field and force that opposes the force of gravity.